over to you. Good luck.
Hello, so my name is, thank you for the introduction. My name is Szymon Drosdzol. I'm a security engineer and a security consultant at DoyensSec. And thanks for joining me today for security presentation, deep in the code heavy at 4 p.m. At the second day of conference. Please bear with me. So our craft are white box security reviews of mostly web applications. So besides the standard pen testing of web apps and dynamic testing, we do a lot of reviews of the code. So naturally, over time, I get to see a lot of these code bases for web apps, for APIs, and all in between. And with time, I started to develop a kind of spidey sense, if you will, for certain patterns in the way that this code is written and organized that oftentimes end up in authorization bypasses, privilege escalations, and that kind of mistake. And this is what I would like to talk about today. So we'll start with a quick introduction, then we'll move to the simplest example of authorization in an API handler that I can imagine, so we are all on the same page what we are talking about when we are talking about authorization in API. And then we will go through different architecture and type patterns that I see a lot in different codes. Towards the end, I will tell a little bit about what I would like to see in a good architecture. And we will talk a bit about how can we harden our API to lessen the blast radius in case such vulnerabilities actually occur. So, introduction. Broken access control is number one in OWASP top 10 for web applications, and I think for a good reason. From our experience, this is found universally in literally almost every code base that we are testing. And I think this is because there will never be a silver bullet of such a class of vulnerabilities. So, while for instance for SQL injections, they have been reduced very, very much over years thanks to usage of ORMs, or for instance, CSRFs has been reduced very much by the way how modern browsers handle cookies, thanks to same-site flags and so on. Access control authorization is way too much closely related with our business model of a given application, and therefore it becomes very custom each time. And therefore the architecture is what makes or breaks the security of a given system in that regard. So a couple of quick disclaimers before we dive into the presentation. All shown vulnerabilities were actually found in the production code, in the wild. The impact varied from medium to critical, and NDAs are still in place, so I had to anonymize all the bugs, unfortunately. So there will be no company names, there will be no API names, no actual addresses. All endpoints names have been converted into something generic and simple enough, like projects, users, exports, and the like. And last but not least, this presentation attempts to be technology agnostic, which means that I am not trying to make statements that certain frameworks, technologies, programming languages are less secure than the others. I rather try to be as generic as possible and just talk about how we should organize our code regardless of the technology. However, you might notice that there is most of the examples that I have today will be in a Python code and Node.js. But again, it's not because they are less secure in my opinion. It's just that most of the code that we are testing over the years was in these two languages, and therefore also most of the bugs that we found was in these languages. So let's start with a very simple implementation of a controller. We have one getter here. And it makes an attempt of some kind of authorization. So what we have here, step by step quickly. First of all, we are getting an ID of an object that we are trying to get from the database. Then we verify whether or not the user is an admin. If so, we also verify if they have the access to the given company ID. If not, we raise a permission denied and we don't allow access. Otherwise, we will fetch this company from the database and return it to the client. So we have two important things happening here. First of all, we have authorization in meaning that we are authorizing that a given user has proper access level, in this case, admin, to access this endpoint. And the other thing that we are trying to do is tenant isolation, meaning that a given user has access only to their own company, but not to the data of other companies, our clients. So who thinks that this is a good way to perform such authorization? I don't see, OK, I see one hand. But most of you think that this is not a good way, and I agree with you. This is not a good way for a bunch of reasons, and we will go through all of them. So first of all, the ifs are written pretty badly, so it can go wrong pretty easily. So imagine, for instance, that this return is we do something very natural and put this return response instead of inside the isAdmin if, just at the end of the function. Let's debug what would happen if the user was not actually an admin. So we will verify whether I'm not an admin. This is false now. So we will fall through the entire if and just return the object to the client. And not only we are not verifying the admin privileges properly, but also we haven't performed the ownership check at all. And of course, you can argue that, OK, this is a logic bug, not the architecture one. But this is exactly my point. If we don't provide any railroads and guardrails to the developers, if we don't provide any framework, the developers over time, for better or worse, will be coming up with different ways to do the same thing. Some of them will be secure, some not so much. So we can see a lot of different ways of trying to perform this in the same code base. We will have different controllers. Some of them will use some helper functions. Some of them will use safe ifs. Some of them will do something else. For instance, we can imagine also such a version for this controller. And just by looking at this getter, we can't really say whether or not it's verifying the privileges, because at first glance, it doesn't, but some developers might come up with the idea to move the check into the fetch company function inside the company service. So it can be actually verifying the ownership, but just by looking at the controller, at the handler, we can't tell neither what's the actual model here or what is the intended model here. So we don't know whether or not we actually want only admins to be allowed here or also users, guests, or whatever. So we've got a bunch of systemic problems here. First of all, we do not provide any framework for developers. It is far from self-documenting. And therefore, it will become unreadable quickly over time. And therefore, it will be hard to maintain also for developers. It is hard or usually just impossible to catch bugs early with static analysis. It is virtually impossible to write a, say, CodeQL or SemGrep rule to check endpoints that are missing authorization if authorization is done differently for each controller. And last but not least, it's fail open, which means that anytime that developers forget about any of these checks, it's just not done, not verified, and we've got immediately a security vulnerability. So I hope it convinces you that we actually should be doing things in a more organized way, let's say it. And so what are the other options of organizing such a code, and what can go wrong with these ideas? So this is a JSONify function that I found during one of our projects. And here, developers have come up with the idea that this JSONify function is called for every endpoint, basically, inside the pipeline, because it has to be called to actually turn the object that we have fetched from the database into a JSON to return it to the client. So maybe it's a good place to perform a last line of defense check of the ownership of the object, to make sure that we are not serving data to users that do not own this data. I like the idea to place the tenant isolation in a code that is called every time, as opposed to remembering about it in every single controller. On the other hand, I'm not a fan of doing it in a JSONify function because it is performed after the database has been already queried and so on. But as a last line of defense, of course, maybe it's a good idea. The problem, of course, is that after going through the rest of this API code, it quickly turned out that the last line of defense has quickly become the only line of defense, right? But still, it worked until it didn't. So why did it stop working? Well, what caught my actually caught my attention is this has attribute if first off. So as you can see here, we are checking if the object that we are trying to serialize has this attribute customer ID before we actually verify its ownership. And if it doesn't, we do not perform this check at all. And on first glance, it makes sense, because what are we supposed to be verifying and checking if we don't have this attribute? However, I start thinking, okay, what if some of the models, for instance, name this field differently? What it's called only customer or customer ID as opposed to UID and so on. So I start going through the code for models, looking for how this customer UID actually makes way into models. And I find this class customer owned, which has this declared attribute function, which is basically a wrapper for a column of type UID, which is a foreign key to the customer's table. So in general, it makes sense. And now we know that every model has to remember to inherit customer-owned to be properly tenant isolated. So of course, if we start looking through all the models, finally we will find the identity model that forgets to do so. And therefore, identity model is not properly isolated from other tenants. And what you need to know about this code also is that it's a very close relation between the endpoints and the models itself. So if we have user model, you can be sure there is endpoint named users. So for identity model, there is an endpoint named identities. And using a single get API request, we can list all the identities from the entire system cross-tenant. So we can list all the emails of all registered users. Not great, not terrible, but it gets worse. As I said, there is very close relation between the endpoints and the data model here. So the developers have also implemented a relationship parameter, and the relationship parameter allows us to query not only the object itself, in this case identity, but also objects that have relation with our identities. So what kind of table can have a relation with identities? Well, there's a table tokens, and now we are not only listing all the emails in the entire system, but we are listing all the session tokens for them throughout the entire system for all clients, for all users, with just a single query. So how does one fix such a vulnerability? The easiest way to do so is to just remember to inherit the identity model. The identity model has to inherit the customer-owned class. And we have the added customer UID property, and everything starts working just fine. However, what I see here is a bunch of systemic problems again. First of all, we've got this fail open ownership check. If we forget to add the inheritance, we just fall through the entire verification and just return whatever cross-tenant. Second problem here is this close coupling of API with the backend data model. So I much prefer and consider much safer APIs where we don't serve directly the models from the database to the API, but instead there are data transport objects, DTOs defined. So developers have this granular control over which subset of the fields they want to show to the end user or end client, and which they don't. This way, fields like value of session tokens, for example, will never make way from the database to the front end. And the cherry on top is the generic mechanism allowing us to explore the data model even further. Speaking of fail open mechanisms, in another project, we have seen the code where developers have decided to create one central place where all the privilege-based access control was centralized. And on paper, on first glance, again, it seems like a good idea. We have this single place, and everyone knows where to go, where they want to define or verify ownership or privileges for a given endpoint. The problem, of course, that first of all, it is fail open. So anytime we forget to define it on this list, in this dictionary, it will not define privileges at all and will be accessible to anyone. And the other problem is that we are talking here about a pretty big API, solid over 500 endpoints. So it does not look like this, which I made readable for the presentation, but more like this. And of course, this is only one privilege, so actually it looks more like this. And the problem is that, of course, it becomes unreadable very quickly. Actually, by looking at this, no one has a single idea what privileges are for each endpoint. And what's even more important, no one has any idea whether or not they forgot to add their own endpoint to that list. So after grueling days of going through the entire list and checking one by one, we were able to identify over 50 vulnerable endpoints. Most of them were not that interesting, but we were able to craft a privilege escalation chain, steal some logs, and some domain-specific actions. Again, we've got systemic problems here. We have forgotten endpoints that don't execute privileges at all. It's a hard-to-maintain architecture. And we still are lacking a solid framework for developers. Despite an attempt to centralize these checks into one source code, what we actually did, we just added one more place that developers need to remember about and go to make their the added endpoints secure. For alt endpoints, I think we need a little bit storytelling. So imagine we are a very small startup. In the beginning, we don't really care about access levels or anything like that. Our clients are also small. But with time, of course, we are getting bigger and bigger clients. And some of them want to onboard their own employees, and they need some required access. They don't want admin control for everyone. So we have the already existing API, on top of which we need to build some access level system, some authorization. Not the easiest task. And I think that actually here, the developers have done it pretty good in general. I like the solution of using annotations for that purpose. Annotations are great because they are both greatly readable for machines and for humans. So it is self-documenting. It is clear what is the intended access level here. And it can be also pretty easily scanned with automatic tools like CodeQL, SamGrep, and the like. So what could have gone wrong here? Well, developers have this compulsion to never introduce breaking changes to their API. So, of course, besides the account v2 list, there's also an account v1 list that does not verify these privileges at all. So it's still possible to just, as a low privilege user, just instead of calling v2 where we will be denied, we can always call just v1 list, and it's still there, and we can list whatever we want. Actually, as an impact we had here, low privilege users can list all tenant users from the system, including their emails. Again, there was some privilege escalation chain by editing invitations roles. So a guest could take over the tenant, basically. And again, we've got systemic problems here, because we have these two parallel APIs basically going on with two different authorization models. We lack the universal privilege execution mechanism. And probably we are missing regular housekeeping. So from what I saw in the front end, the v1 endpoints weren't actually used that much. Or, I mean, they weren't used, by that I mean they weren't used at all since forever, but they were still lurking in the API because no one ever, took the time to take a look and verify whether or not they're still needed. So regular housekeeping, I think, is also a part of our system that we need to remember about. Yeah, and the takeaway here is that authorization and access control can never be opt-in. Actually, I'm having a similar discussion as we speak, basically, on Slack, with one of our clients where developers had thought it would be a good idea to use feature flags to actually introduce authorization. So authorization is basically opt-in for a client. Inconsistent design is another problem that comes up a lot. And it comes in all shapes and sizes. I think that if I was to identify one that comes up the most, I think it's this one. One could argue that the very first examples that we're doing, the simple one, also with time will become inconsistent design sooner or later. And usually they are very hard to actually show on a presentation because they're all about the abundance of code that is doing everything in a messy way, so it does not make for a readable presentation. But I have one example that I think is actually pretty boxed and actually pretty instructive in how these kind of problems introduce vulnerabilities. So what do we have here? We have here a two-layer API, basically. First of all, there's a proxy view, which is the front end, which is the one called by the clients. But the proxy view does not implement any business. It just, proxies it to the API view in the backend, which implements the actual business. And if we take a look at this, we will see that both of these views implement some kind of authorization. They are both authorization aware. And I don't hate this idea. Actually, I do like when all the layers of the system are authorization aware. However, the problem here is that despite the proxy view having the permission classes, it has this allow any, so it will just allow anyone to access, while the backend requires this permission retrieve, which wouldn't be that bad, but also if we find another view, this time for projects, it will turn out that actually it's the project view now that is requiring the root admin role, while the backend one only requires is authenticated, so it doesn't care about the privileges of a calling user, it just cares that you're authenticated at all. Another problem that you can see here is that here we have permission-based authorization. It talks about the retrieve, while here we have the role-based authorization, which only adds to the mess of the entire solution. And as you can imagine, the number of possible combinations is rising quickly. And of course, you have to remember that these views, these classes, are only neatly, placed side by side in my presentation, while in the real code base, they will be in some completely different files, folders, or even repositories. So actually, what we are looking, usually we look just at the API view. We see that, OK, there's a permission class is authenticated. And we have no idea, again, what's the intended and what's the actual authorization model for the entire thing, for the entire chain. And of course, with such a design, it's only a matter of time when we find a pair of proxy view and API view that allows any in the front end and just is authenticated in the back end. So we have numerous endpoints that just reveals domain data to our low-privileged users. And there was also some possible cross-tenant leaks. Their impact was actually limited by using GUIDs to identify objects, which is also a spoiler of one of the hardening ideas. Again, we've got systemic problems here. We've got a problem of multiple ways of doing the same thing. We have unclear privilege model. There is role-based authorization. There is privilege-based. They all mix and match together or don't match. And we've got this inconsistent authorization enforcement location. We don't know where actually to look when we want to find out what is the intended and actual model for the particular endpoint or controller. So, OK, we have some time. So the last two are a little bit more technically involved. And Some say a little bit more specific, but I think that we also can learn quite a lot about architecture from them. So here we have a Node.js example of yet another two-layer API. We are looking at the handler of the client-facing one. And again, it's basically not implementing anything. It's just responsible to forward the query to the specific API, microservice, whatever in the backend that is not customer-facing. And this IP location is actually very boring technical endpoint. It isn't even supposed to query database at all. It's just supposed to convert our IP into a location. So for instance, if we take the IP of us from here, it should return something like Kraków, Poland, or something like that. So this is how it works. For instance, if we give it some valid IP, it will forward this IP to v2 employees location API in the backend, and will forward whatever response this backend has returned. So what will happen if we actually place instead of IP, place a path traversal payload here? Well, it will be normalized into v2 employees endpoint, and this is the request that will be sent to the backend. And it turns out that v2 employees is an actual endpoint in the backend, and we will just forward the response to the client. And here what the developers did is that the entire authorization was placed in the front end, actually. So the microservices in the backend never cared about the actual authorization, about filtering anything at all. So this is just a list of all employees cross-tenant again for the entire system. So a simple utility endpoint can become a gateway to any backend path and to listing cross-tenant data from the system. And we have a bunch of systemic problems here again. We lack any incoming data validation. No one cares to verify whether or not the incoming IP actually looks like an IP. We lack any defined outgoing data model. So if developers took time to define that IP location should return an object with one field named location, then it would fail if it started trying to return, say, employees' data. And we are lacking the authorization in the internal services, in the backend microservices. So anytime there's any bypass of the front end via path traversal, via server-side request forgery, some authorization bypass, they immediately become critical vulnerabilities because the rest of the system is not authorization aware at all. Parameter pollution is, I think, the bug that I'm proud the most from this list. I also like it because there is a bunch of things that I actually do like about this code. So as I said, I generally like implementing APIs and authorization authentication using annotations because they're readable for both machines and humans. So what do we have here and what do I like at this code? Well, I do like that we have a clear route location. We do know at which path it is available, what methods does it expect. We have clear authentication and access level for users that we require here. We have authorization, which here means tenant isolation, actually. And we verify authorization in this particular case for the project ID. And we have parameters filters, so we know exactly what kind of parameters do we expect from the JSON object in the post body. So this is what I like. So what went wrong here? Well, what went wrong here is this API authorized implementation. So what we need to know here, first of all, in the implementation of the handler. As you can see, it uses these request values here, which is actually a part of the Python framework used here. And it's kind of a weird beast, because values is a dictionary that sums up all the parameters, both from get parameters and from the post body. Which I think is not a great design idea, actually, and we will see why in a moment. However, for the API authorized, the developers wanted to be as generic as possible. So to retrieve all the possible parameters from all the possible places, they have developed this request values function, which not only takes these request values that we have seen a moment ago, but also then it is also added request forms items, and all of this is merged, squashed into one single dictionary. So this is how this endpoint is used, as designed. We create a simple post. There's a project ID which we are editing, and we add the node to it. And then we can see that we get this project ID in a handler using request values, and is 456, and also this generic mechanism also gets 456. The problem, however, comes when we will add another project ID parameter as a get here. So in this particular case, it will turn out that request values actually prefers the get one, while in the API authorized, it will be overwritten by the post one. So now suddenly we are editing a different object that we are verifying parameters for, and therefore we've got the vulnerability because we can just give 456 because we control 456, but actually edit 123 and any other object in the system. So again, we've got systemic problems here. We have this overly generic parameter retrieval. I prefer generally implementations where it is much more locked in, where developers has this granular control over from where, what kind of data are they taking. But if we decide to use this over generic parameter retrieval, we need to make sure that we are actually using it all over the place. If we are doing this in some places but using other mechanisms somewhere else, we can have these corner cases that can become the vulnerabilities in some cases, like in this case. And the problem also is the predictable object IDs, which makes the exploitation, especially at scale, much more easier for an attacker. So from all of this, what we would consider a good architecture? First of all, we want the architecture to be self-documenting. We want to be sure, just by looking at the endpoint and the controller, what is the intended shape of authorization and what the actual is. We want it possibly fail close, so in case anyone forgets about a check or to define the access level, we want the default to be only admin access or just no access at all. We want a single way of doing things. We don't want these free competing implementations of authorization, of parameter retrieval, and so on, because this just creates corner cases that can be exploited. We want to ensure that authorization rules are global for the entire system. And we also want the life of developers made as easy as possible. So we don't want them to remember to go in these free places to remember stuff, to modify this list and that list, and also implement properly the endpoint. We want the framework to do it for them and just enforce, good definition of what is required for this particular endpoint. And also, we want tenant isolation possibly at data layer. Thanks to that, when developing endpoints and services, we are already sure that we are only operating on data for a given tenant, and we don't have to worry about cross-tenant issues at all. We can also harden our API a bit. We want to make sure that we are only returning necessary data, so define your DTOs, make sure that that's only data that our front end needs, and make sure that we are not returning any data like secrets, like password hashes, like invitation codes, API keys, besides the creation, of course. Enforce the authorization for all microservices in the system. Therefore, any bypass in only one service that does not become a critical vulnerability for the entire thing. Validate input data, enforce data types, parse integers and numbers when you receive them. This way, you get far more control over what actually makes way into your system, into your services, and into your business. And the last thing is something that did not come up directly in this presentation, but I would strongly argue that mixing super admin services and like internal endpoints that bypass the tenant isolation are a bad practice. One obvious reason is that any privilege escalation becomes a cross-tenant issue automatically, because if we can become a super admin, we can bypass any limitations of our company tenant and so on. And of course, I know that many of these things may take a lot of time. So, of course, not much of the teams can just sit down and rewrite the entire thing with this. So, what can we do with limited time? First of all, we need to identify the most impactful endpoints and refactor them, possibly. If our infrastructure or architecture allows to at least have some repeatable patterns that we can scan with CodeQL or SemGrep. I'm a fan of SemGrep, for instance. Then we should do it. Here you have an example of the rule that I wrote for one of our clients to catch all the endpoints that forget about authorization. Going quickly through that, we have this pattern for router.verb, so for instance, get, post, and so on. So using this pattern, we get all the endpoints handlers in the entire code base. But we filter out the ones where developers actually remembered to do authorization properly. So as an effect, we get the list of all the patterns that are missing the authorization. So it's a great way to very quickly get all the suspicious endpoints. We can utilize these rules in the CI/CD and create control that could be improved over time by refactoring more and more endpoints over time, and of course ensure that any newly added endpoints adhere to our new rules. And I think it's a good idea to migrate to GUIDs as opposed to integer predictable IDs. I know that this kind of sounds like a security through obscurity thing, and it kind of is, and I would never advise anyone to rely only on this thing. But the experience says that, in general, any vulnerabilities that were critical with integer IDs will become just highs with GUIDs. Anything that would be a high will be probably medium with GUIDs, and so on. So that's all I have for you today. Hopefully it was somehow useful. And if you have any questions, then please.